Okay, so today's lecture is going to be about mechanical translation, and specifically we're going to be looking at some components in more detail and characterizing what flow and effort each one possesses. So if you recall from last class, we had energy to be defined as simply the integral of the effort times the flow with respect to time, which, if we want to specify this definition with respect to mechanical translation, then this integral is simply the effort, which would be some characteristic force, times the flow, which would be velocity. And we've taken this integration with respect to time. Now, we looked at the example from last time. One case of a dissipative element. So if we want to calculate dissipation, E dis, then we can recognize that it is going to be this similar calculation where we integrate the characteristic effort or force times the flow, here being velocity with respect to time. Okay, so another example that we're going to take a look at as a component that is dissipative in more depth is the damper again. So as a first case, let's look at a damper, also known as a dashpot. Okay. So if we just draw a representative picture of what that damper would look like, where here we have the effort, so F2, F1. For right now, we don't have to worry so much about the actual direction or sense that we're drawing these flows, but rather just recognize that they're present at each end of this element. And also at state 1, this left-hand side, is we have some representative flow, and on state 2 we have a representative flow V2, such that the overall flow here, V, is going from state 1 to 2. And for the effort, we recognize that the effort is the same, F1 equal to F2. Now what we want to take away from this is really characterizing what relationship this element, this damper, has with respect to dissipation. So how is it dissipating energy? All right. So one thing we do know is the constitutive equation. Okay. And that is that if we want to see how the effort changes as a function of that flow, so as a function of the flow V, then we can write, or draw rather, what that relationship would look like. So here, if we have the flow, and on the x-axis we have the the flow velocity in the x-axis, the effort force here in the y-axis, then we should expect that the relationship here between the force as a function of the velocity will be linear. Okay. For viscous fluids, where the slope here between F and V would be the damping coefficient. Now, What if instead we don't have a viscous fluid? Then this relationship between F and V becomes nonlinear. So if I can just sketch that on top here. Then it is possible to obtain a nonlinear relationship between the effort force, F, and the flow velocity. Okay. One other aspect where we would have some dissipative relationship here between F and V, I'll draw it right here next to it, is in the case of dry friction. Okay, so still this is F, this is V. Now in the case of dry friction, we have this discontinuous relationship where the height here that is given between F and V is equal to mu times, let's go with N being the weight or normal force of the object or rigid body. And down here this would be just negative mu N. And mu here would be your coefficient of friction. Now this relationship in between F and V is true for Coulomb friction. Specifically, we can say dry friction. Okay. Now, one thing we can make a note here at the bottom, all right, is that in any case where the product of the flow times the velocity is greater than 0, then this would indicate that the power flow is to the element or component, all right, element slash component, which is just a simple statement that we have dissipation of power and energy. Okay. Now, one of the things that we can make a note of, okay, using this fact, is that the curve here between F and V then must lie in between the first and third quadrants, okay, in order for us to have dissipation. So let me write then, therefore, whenever the product of F and V is positive, then that is only true in the first, where we have a positive effort and a positive flow. Or if we have a negative effort and a negative flow, then the result is a positive power, aka dissipation. Therefore, FV curve must lie, okay, in the first and third quadrants to get dissipation. So if I can, I will, let me just draw another figure down here. Of my FV plot, where we can say, so we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. And we have dissipation in 1 and 3. Okay, and in quadrants 2 and 4, those act as sources. So the opposite of the case where we have dissipation. Okay. Again, to reiterate back up here is that we can determine this energy dissipation and resulting power using this integral. Okay, so let's do another example. Okay, where again we're going to incorporate the things that we learned in last class as well as what we just covered with respect to calculating dissipative power. So this would be an example of a stopping car. Okay, so we're going to be given, okay, a car with velocity v naught. So let me draw a sketch of what this would look like. So this car traveling down the road this way, so it has some velocity v naught, and as it tries to slow down, its brakes lock and it skids to rest. Okay, so what we do know is that the velocity, okay, at t1, okay, is equal to v naught, and at t2, when the car eventually comes to rest, is at 0 velocity. All right, and what we need to find, all right, is the length of skid. So, so you can think of this, v naught is the velocity of the car just before it applies its brakes. Okay. So for our solution, all right, is again, we can make use of our conservation of energy, where we have, you're right, using conservation, all right, so here we have P1 minus P2 equal to the change in energy stored plus the dissipative power. Okay, so at let's see, if we look at the power quantities here at state 1 and state 2. So at state 1, all right, when the car is traveling and right before it brakes, so actually let me back up. We should define our system boundary here. Where this would be when the car applies its brakes and it skids to a stop right here. So notice how if we look at the power, okay, there is no power coming into this system, so there's no effort. So the power P1 is 0. Okay, so let me write here no effort. And furthermore, at time t2, the car has come to complete stop. So let me write here, car stopped at state 2. So those two quantities equal to 0. Okay. And therefore, I can simplify this to be just the change in energy, E dt plus P dissipated equal to 0. All right. Now, what we do know is the energy that is stored. Okay, so we know that the car is traveling at some initial velocity, v naught. There is no potential energy. So as it relates to E here, EKE plus EPE, where there is no potential energy. However, the kinetic energy that is stored in the system is just 1/2 mv squared, v naught squared. All right, where again, I didn't annotate this in my original drawing, but let's say this car has some mass m. All right, so what are we left with? And we need to define what this quantity is, our dissipative power. Okay, so as we just finished talking about, we can calculate this dissipative power. Okay, so as you recall, it is simply the integral of F times V, or we can just simply write power P dissipative. Since power is the integral of the energy, it's simply F times V, where this F here is the dissipative power, force. Okay, and this velocity is a function of time. Now, what is the dissipative force here? Well, that is nothing other than the friction that is felt between the car and the surface of the road. So if we assume Coulomb friction, as we defined it in the previous page, then this further simplifies to be mu times, and for the normal force, let's just call it mg, okay, for simplicity, since we have m already representing the mass of the car, times the velocity, vt. Okay. So, let's see. So, the next step, so we have the dissipative power, we have the change in kinetic energy, which we didn't. So let me summarize this in the next line to be d dt of 1/2 mv naught squared. All right. Plus mu mg vt equal to 0. Okay. So what I do need to carry out here is, in order for me to obtain, so unlike the first example that we did last class, we're not going to derive the equations of motion, but rather we're going to integrate the kinetic energy, okay, from time t1 to t2, all right, and that's going to allow us to then solve for some amount of distance. So that distance would be the length of the skid. So remember that this is my change in kinetic energy. I'm sorry, my kinetic energy E, KE. So this is going to be, in order for me to get KE, I'm going to integrate from T1 to T2, okay, with respect to time. So integrate 1/2 mvt dt So the mass, let me bring out the mass and the 1/2 out of the integration. From T1 to T2, V of T dt. Oh, okay, I see what I realized. So this should be just V. We're going to integrate this. So when we integrate this, this is going to be 1/2 m. This is V at T2 minus V at T1. Now the velocity here at T2 is 0. The velocity at T1 is V naught. So at T2 it's 0. At T1 is V naught. And we know this because right before the car applies its brakes at T1, the velocity is V naught. So we're left with here being 1/2 m V naught. What am I missing? The square. So this should be V of T minus V of T1. So you should be squared quantities. So V naught squared. And the minus. So we have a negative 1/2 m V naught squared. Okay. So what we've done is successfully integrated the left-hand side. Now whatever, so if I want to be consistent, if I move this over to the left-hand side, I also need to perform an integration, as I've done here. So on the left-hand side, this is going to be the integral T1 to T2 of mu mg v t dt. Okay, so what am I going to get? So the mu and the mg, these are all just constants. Integral from T1 to T2 of v t dt. So if I integrate this, then I should be left with, actually, before I even do that, what I can recognize here is that Vt is equal to dx dt. So if I substitute that in before I integrate, this is mu mg integral from T1 to T2, then this is the integral of dx, which now by this transformation I need to update the limits of my integration to be now from x1 to x2. So finally, completing this integration, this becomes mu mg from x2 minus x1, or let's just call this dx, since really all we're concerned with is dx, the length of the skid, which this term represents. So if I go back up here to my define, this is dx. This is the parameter we're trying to look for. So what I've done here is, and let me just summarize, is we had this derivative term that I integrated, got negative 1/2 mv naught squared. Now this term is going to be also integrated, which we did here. So what we're left with is negative 1/2 mv naught squared. That's this first term. Second term is plus mu mg delta x equal to 0. So again, this is the term that we were trying to solve for. So if I solve for delta x, one thing I can recognize right at this step is that the m cancels. And if I solve for delta x, so I move this term over to the left-hand side and divide by mu times g, then I am left with v naught squared, right, over 2 mu g. So this would be the representative length of the skid. So just to recap, again, we made use of the conservation of energy and looked at the system boundary, okay, that we defined for the system. Okay, but we took a different approach in that what we got from the conservation of energy, okay, we integrated the terms so that we can get quantities here of interest, in this case being the distance that is traveled by the car from state 1 to state 2. And then that allowed us to then solve for delta x. Okay. So moving on. So that first element or component that we looked at was the dashpot as related to mechanical translation. So now let's look at another component, the linear spring. And really, the nice thing about this is that we can then derive other relationships that also exhibit what you're more familiar with is Hooke's law for other applications such as beams and rods that have a representative stiffness or to the material. So in this case, we have potential energy that is stored. Let me write here. Okay. So if we draw a representative element of a spring, or again, let's draw the effort. If we call this my state 1, state 2, and include the flows. Now here, in the interest of the linear spring, the flow variable would be displacement, x1, x2. And again, let's write the effort and flow variables. So now we have flow x to be the distance x1 to x2. So here, let's just make it clear that this is the displacement, okay, from the equilibrium position. Okay, and then we also have for our effort variable F1 equal to F2. So let me make a note of that. Displacement from equilibrium position. Okay. So in the same way that we did for the damper, okay, let's write the constitutive equation. Okay. And so for I should write F equal to Fx. So for our linear spring here, we can characterize the force to be a function of x, so the displacement of the spring. So let's draw that relationship. To characterize its curve. So here we have x on the x-axis, force of the spring with the effort, and the y-axis. All right, and so we should expect, here we already brought up as a linear spring, but we will also make note of any nonlinearities that exist for other types of springs. But here we would expect that the relationship between the displacement and the force is linear, at least for the case of it obeying Hooke's law. So here the slope is k. Okay. And let me draw for the case where we have a nonlinear spring. So let me write here, this one's linear. The other one would be nonlinear. So the nonlinear case would be, for example, one type is a hardening spring. So in this case, this force is not proportional to the displacement. So it rather has this nonlinearity to the force, between the force and the displacement. And then here we have this linear relationship for a linear spring, so we can calculate the force to just be that slope times displacement x. Okay. Now, I mentioned that this has some potential energy stored, and the way we can calculate that energy storage is by looking at the area under the curve. So let's say if we just look at this section of the curve, look at this area. So let me make a note of it over here off to the side, that the area, okay, is analogous to the stored energy, which can be calculated as being the integral of the force times the distance, dx. All right, so this is stored energy. All right. And again, the way we calculated this was one of the ways we can relate it back to where we're taking the integral of the effort with respect to our displacement variable. Okay, is how we calculate energy before. So once again, for a linear spring, the force is simply k times the distance, x. So this is true of Hooke's law. Okay, and therefore, if we want to just carry out that integration, then we can calculate the energy to be the integral of f dx, as we've laid it out here, where if the F force is just k times x, and this is the integral of k times x dx. Okay, and if we complete this indefinite integration, then we're left with 1/2 kx squared, okay, plus some amount of energy, initial energy, E naught. So in some cases this could be 0, okay, but if we have some residual energy stored in the spring, then we can add it to the energy calculation here. Now the case where we can relate this example to other cases is, let's say, for example, we have a cantilevered beam. So let me write similar applications. Let me write, let's look at example A, cantilevered beam. So if we have this cantilevered beam initially here, but if we apply a force right at the tip, some force F, okay, and let's assume that this has some initial height h, which we can also characterize in its cross-section. If we take a look at its cross-section over here off to the side, this is height h. And if we're looking at in this view, we can also say it has some width b. All right, and initial length L. So by applying this force at the tip, then we can characterize the deflection. So this is obviously exaggerated, but just to show that the deflection here of the beam is given by some distance x. Maybe you're familiar with using the term delta to characterize that displacement. But nonetheless, we have a way to calculate that, or at least relate the displacement to what this force is doing, which is causing some bending moment on the beam. So we know that, let me see if I can include it over here on this right edge. So we know that the deflection, or at least the second order of the deflection, where again this term is the second derivative of the deflection, so it's a function of x. It's related to the bending moment by m over EI. So E is the modulus of elasticity, also known as Young's modulus, and I here is the moment of inertia of the cross-section. So at least for a rectangular cross-section, we know that I is equal to BH cubed over 12, but again, that's important, but we need to integrate this a couple of times. E and I are just constants, but here M, which is also a function of x, we need to integrate once. We get the slope equation. Second time, we actually get the deflection x. So if we need to integrate twice, let me write that here. Integrate twice. Then we get the fact that the at least the maximum displacement delta, let's just call it x here, since we use x. So the maximum displacement here at the tip of the beam comes out to be FL cubed over 3I EI. Okay, and so how does that help us? Well, if this is our displacement x, all right, if I instead take this equation and I solve for F, then I get F equal to 3 EI over L cubed times x. So what I can take away from this is that this term right here, we'll call this K of the beam. That K term represents the stiffness of our cantilevered beam, which is, if we want to consider it similar or analogous to the spring relationship. So it exhibits a similar linear relationship that a normal spring would have. And we can do this again for another example application of a elastic rod. Okay, so imagine we have this rod. Okay, it's the area is constant, area A, and we have a equal and opposite force F on either end of the rod. Okay, and then let's say that this rod has some initial length L, but from this tensile force then we would expect some elongation, so let's characterize that by some delta L. Okay, so let me do this. Let me call this initial L. This is delta L, and therefore overall length L, or final length if you will, is simply L naught plus the change in length due to elongation. And so from here we can use, because it is an elastic rod, and as we've seen already in other cases where we are obeying Hooke's law, then we can use Hooke's law for stress to be this, where we have the normal stress related to the strain by simply the modulus of elasticity. And if we expand this out, we can calculate stress to be just force divided by the area, the cross-sectional area. And as long as we can agree that the material is homogeneous, then we can define this normal strain, okay, by calculating it as the deformation distance, in this case delta L, or the initial length L naught. Okay, and finally, if we solve for force F, then we end up with E times A over L naught, okay, times delta L. So, box this in. So then once again, we have here, this is our representative displacement term, delta L, which is just X, and here is our, we'll call this K for the rod, our representative stiffness. So all these examples, make use of Hooke's law and the fact that we can represent the rod or the beam just like spring elements, okay, that have that linear relationship for this curve. Okay. So one more case, I should say two more. One of them is a short one, is just looking at mass. Okay, so this is our third component. So let's look at mass. All right. So very simply, if we draw just a representative mass element, where we have our efforts here again, F2, F1. We have our flow terms. So in this case, we have V2, we have V1. And so we have overall flow here from V1, which if this mass is the same, we're not saying it's changing from state 1 to state 2, so it's moving as one homogeneous unit, V1 equal to V2, so the flow is the same. However, the force may be that it experiences, so the force flow here, F, is F1 to F2. And just like in the other cases, we can define our constitutive equation. So we're trying to characterize here the relationship with the force here, the flow term, V, and we want to see how it relates to the momentum, our momentum term. Okay. So again, recall that we can calculate the momentum, P, by integrating the force F with respect to time. All right, so let's not forget our momentum variable. All right, P. So at least in the case of a Newtonian or classical relationship of the momentum for this mass, there is a linear relation. Okay, so let me write the relation first and then I'll define it. So I'm going to say, therefore, the flow here, velocity, is simply the momentum divided by mass. Obviously, we're more accustomed to seeing this momentum calculation as mass times velocity, right? But nonetheless, still the same. So this is our, for linear, this is Newtonian. Our classical relationship. All right. So from here, I can then calculate the energy. Once again, we can make use of the, let me see, our energy calculation. So we can use now the other equation that relates the flow to the momentum variable. So here our flow variable is V, and we're going to integrate with respect to change in momentum, or P. So in place of V, we will insert this relationship. Okay. Or let me see, I should say, rather, let's see, I don't have my notes from last time. Let's replace this term dP. So dP is equal to m times dV. So this integral rather becomes m times the integral of v dV. All right, so here this will allow us to integrate with respect to the flow variable as opposed to our momentum. But nonetheless, this is still representative of our linear relationship here that we have between flow and momentum. So if we carry out this integration, then we get E is equal to 1/2 mv squared, again with some constant of integration, E naught, in case we have some initial energy. All right, and that's really it for mass. So essentially we have kinetic energy. Let me write that here in parentheses. KE stored. All right, and our last element here that we will talk about is looking at sources. So the way we opened up the lecture in talking about dashpots and them being dissipative elements, and the idea of sources came out from the second and fourth quadrants of our flow versus velocity, or I should say effort versus flow plot. Then we also have this presence of energy sources, okay, where we have some amount of characteristic effort due to the energy source, and and as well as an energy source due to the flow. So the way we can characterize energy sources is using the S term. All right, and so we will have a SF okay, so this is, so F of t provided by source and so if F of t, or our effort, is the source, then that makes our flow variable, V of t, arbitrary. And it will be based on the system response, or characterized by the system response. Okay, and in a complementary way, if instead our source here, S, is our flow variable, SV, then Vt is provided by source, okay, and F of t, our effort variable, will be arbitrary and based on the system response. Okay. So one thing I can add here below each one of these, okay, and provided they both provide energy to the system, okay. So in the case of SF, here where Ft is provided by the source, okay, we can also say that the flow variable Vt is based on, so we said it was arbitrary and based on system response, and so more specific, we can say it's based on the system's admittance. Okay, and here where F of t is arbitrary based on system response, that will be based on, more specifically, the system's impedance. I guess I should have not repeated myself as much, but there we go. Okay. So I did mention in either case, both do provide energy to the system. Okay, that's why we can characterize them as energy sources. Let me just write that here. Okay, both provide energy to the system. Okay. All right. So one of the last things that we can finish up with this topic is just to go back to a little bit about mass, okay, and the idea that we can characterize masses. Let me see. Let me go ahead and stop here. This is a good stopping point. We can continue this discussion when we meet up again on Tuesday. So I'll be back in class. Okay, that'll be Tuesday, September 10th. Do keep in mind that there is a quiz. So let me write that. There is a quiz 1, on Tuesday, September 10th. Okay, and that will be over power and energy. So much like you saw in the examples, so we saw one example today with the car. Last class we had the example of the spring mass damper system. So we're only going to focus on mechanical translation. So in essence, just know, we're going to be working with effort of forces, and where your flow variable is your velocity. Okay, so if you kind of look at those two examples that we've done in class, that'll be exactly what your quiz will be over. All right. Okay, we'll see you on Tuesday. Bye-bye.